So thank you very much. Thank you all for being here. And David, it's up to you.
Very good. Thank you, Luca, and I very much appreciate the invitation and everybody's attention this day. I'm going to be speaking about our work over about the last 25 years or so, when we saw the development, the continued development of high performance computing and capabilities to model material microstructure at mesoscopic scales, with emphasis on, let's say, the last 10 years or so of advances that we've made in using computation to be able to rank order microstructures with regard to fatigue resistance, ultimately leading to enhanced fatigue design capabilities. So some key points that I'll make in my presentation today. First of all, I want to focus on what we call microstructure-sensitive strategies. That is, we incorporate realistic microstructures and we compute mesoscopic quantities of interest. We call them fatigue indicator parameters that enable us to compare fatigue resistance of microstructures. This is sort of a material selection design improvement type of capability. We focus on fatigue crack formation within the nucleant grain or phase and early crack growth within the microstructure, so-called microstructurally small fatigue cracks. I'll also discuss a bit on some work we've done recently on multi-axial fatigue, which provides designers some information to be able to generalize to combined stress states that are actually seen in design of components. It's important to realize that computation at the microstructure scale is quite heavy. It's quite time intensive. So we've been exploring the last 3 or 4 years the use of data science to accelerate, and also incorporating uncertainty quantification as a key element in the forward projection of microstructure property relations. And so at the end, I'll discuss a few horizons, things that are good opportunities for you and others to work on in the future. I'd like to acknowledge a number of grad students and postdocs for the last 10 years or so, as well as support from U.S. National Science Foundation, a materials design company, Quest Tech, Air Force Research Lab, Navy Labs, Simulia, Boeing, Naval Research, and Air Force Office of Scientific Research. So there's a lot of complexity in modeling fatigue crack formation and early growth within a microstructure. And of course, when you're in high cycle fatigue and very high cycle fatigue, it's extremely important to understand the role of microstructure, because crack arrest, favorably oriented grains or phases to form cracks, etc., are all heavily dependent upon microstructure. So that's a regime that's highly microstructure dependent. Ultimately, fatigue crack formation in ductile metals boils down to irreversibility of the dislocation network, whether it's the incipient formation of a crack in a disrupted lattice or the propagation of a crack due to and fro irreversibility of the dislocation network. There is much uncertainty or imprecision in the very definition of fatigue crack initiation. When you first learn the subject, you learn about so-called fatigue crack initiation, maybe a crack of the order of size of 30 microns or 50 microns. It's rarely specified in terms of the size relative to the microstructure, for example. And so we insist on understanding and quantifying the stages of formation and growth as a means of being more quantitative about the process of fatigue crack initiation. Classical initiation criteria, Baskine's law, Kaufman-Manson law, they typically don't incorporate microstructure. Rather, the role of microstructure is reflected through the law parameters. Now, the other thing that's very important is a crack that forms in a nucleant phase or grain is subject to elastic plastic fracture mechanics conditions. Even though it's a tiny crack, there's lack of similitude of that crack, typically large scale yielding, and quite anisotropic elastic and plastic behavior. So using linear elastic fracture mechanics, for example, for small cracks growing along slip bands and crystals may not be advisable. So we choose a strategy for surrogate driving force computable quantity of interest measures that is able to reflect these considerations. The other thing is computability. It's difficult to compute local driving force in the presence of shielding of, let's say, dislocation populations and heterogeneity of the underlying microstructure. And you have to remember that whatever you do, if you're comparing microstructures or computing a number of statistical cases, you have to have a computable scenario. So again, for this, we use computable quantities of interest. This is a concept that's well understood in the literature and statistics. About 10 years ago, a student of mine, Craig Prisbala, who's now with the Air Force, generated this in his PhD thesis. It's the materials design development role of extreme value fatigue simulations to understand minimum lifetime, to rank order microstructures with regard to minimum lifetime. So let me use my laser pointer here. We start with generating a number of statistical volume elements. These are periodic volume elements that encompass enough grains or phases such that it captures important two-point or radial correlations between microstructure that produces high driving forces, but small enough so that it's not a representative volume element. It turns out that in fatigue, a representative volume element is huge, beyond computability typically. We then take an ensemble of n of these statistical volume elements. We compute the extreme value response surrogate driving force measure of interest, so-called fatigue indicator parameter. For each of them, we populate a cumulative distribution function, as shown here. It's a cumulative distribution function of the simulated fatigue indicator parameters. And then we're able to consider two-point statistics of correlations between the extreme value site within the microstructure and the neighboring microstructure to understand mechanisms. We're also able to compare different microstructures in terms of whether this CDF is shifted to the right or more to the left. Obviously, cumulative distribution functions for a given imposed loading condition that occur to the right have higher driving forces and therefore are less resistant to fatigue crack formation. We can take that information from these extreme value cumulative distribution functions. In this case, it's a so-called Gumbel distribution, which is one of the 3 extreme value distributions. And then we can iterate the process route to improve the microstructure for purposes of materials design, or we can select top candidates of process routes or microstructures for a given composition. In terms of the choice of our quantity of interest that we compute, instead of computing in fine detail something like the cyclic crack tip displacement of a small crack in a single crystal or a single grain, we compute a fatigue indicator parameter at a given a finite volume of sub-grain scale. As shown here, it's a mesoscopic strategy. This blue vertical line lies between dislocation patterns and the grain size in a polycrystal. Specifically, we're interested in computing over a quantity, over a volume in the order of maybe 10 to 100 microns cubed, subgrain size, in order to compute the non-local localized slip type of parameter that constitutes the FIP definition. It pertains to nucleation and early growth within the nucleant grain or phase over that fatigue process damage zone. So this is a mesoscopic damage process zone concept. Doing this by averaging over some finite domain, we provide regularization to the solution, so mesh sensitivity, and we also are in consonance or in agreement with the physical concept of a finite size of a cyclic damage process zone to form a fatigue crack, typically in the order of microns. The 2 fatigue indicator parameters that we've looked at rather extensively are based on the so-called Fatimi-Sosi concept of the maximum plastic shear strain amplitude or the maximum shearing rate amplitude on the slip plane, modified by the influence of the peak normal stress, the peak tensile normal stress to that plane. And the argument going back to Fatimi and Sosi for intermediate crack initiation links is that somehow the effect of the normal stress is to assist in the propagation of a crack through a microstructure. This is for transgranular to the left, for cracks that arise due to slip impingement on grain boundaries for positive R ratios, positive load ratios, where you have an accumulation cycle by cycle of dislocation piles up to the to the grain boundary, as shown at right here. We use the net plastic strain on the slip plane and the peak normal stress to some finite length of grain boundary segment. So it's a Zener-Stroh type of mechanism. But typically the cracks will form due to disruption of the grain boundary and a release of the constraint on slip in the adjacent transgranular region. So the cracks row up the transgranular slip plane away from the interface. And you see these typically in literature where people have done SEM images of failure sites. And again, the cyclic plastic zones and the cyclic plastic strains that are used to compute these quantities of interest are averaged over damaged process zones using a slip banding technique that we've published on the order of 10 to 100 cubic microns typically. Once we select a volume average size, a size scale for the damaged process zone, we use that consistently for various microstructures because we want to compare apples to apples when we compare microstructures for relative resistance to fatigue crack formation. Now, the Fatimi-Sosi transgranular fatigue indicator parameter, that surrogate driving force measure, is indeed a surrogate for the crack tip cyclic displacement, the cyclic crack tip displacement, CTD, as shown by Gustavo Castelluccio and I in the International Journal of Fracture in 2012, where we inserted cracks either in a single crystal, a homogeneous single crystal, or in a single crystal that had a slip band that carried all the deformation, the cyclic plastic deformation, aligned for single slip, as shown here at upper left, with the crack running along the interface between the slip band and the elastic matrix. And in both cases, for both cyclic shear loading of the crystal and for mixed mode loading, you can see at lower right that the cyclic crack tip displacement measured just 1 or 2 microns behind the crack tip correlated very well with the Fatimi-Sosi parameter. So we argue, and this is an extension of some work by Jean-Yves Berard and I back in the early 90s, that it's very useful to use these surrogate measures, which are easily computable at coarser scale. We also use a small crack growth law, as shown in the middle. DADN for the microstructurally small crack is some irreversibility factor phi times some constant A times the computed FIP minus the threshold CTD. The threshold CTD is taken essentially as on the order of the Burgers vector, so eta is approximately equal to unity. And we see that the FIP then serves as a reasonable surrogate for the delta CTD. And I'll talk a little bit later about how we've used that in small crack growth laws. There are 3 thresholds in this kind of a model. One is the absence of plasticity, or the absence of microplasticity within favorably oriented grains or phases. That drives the FIP to 0 locally. The other one is if the CTD, the delta CTD, is less than the threshold value, then we call that the microstructurally small crack threshold. And then, of course, we're all familiar with the delta K threshold concept in linear elastic fracture mechanics, which in general pertains to cracks that establish similitude with respect to the size of the cyclic plastic zone relative to the underlying microstructure. That takes about 5 to 10 grain sizes for the crack length in general. When the crack length is on the order of the microstructure, or just a few microstructure units, grain sizes, for example, we have the lack of that similitude. So we have to be careful, and we have to employ appropriate small crack growth relations. In high cycle fatigue, as shown at lower right, the lifetime, the total lifetime is dominated by the incubation, let's say the formation of a crack and early growth within the nucleate phase. And of course, as we transition into low cycle fatigue, the small crack growth relations and microstructure become more important, and ultimately the long crack as well. We use Dream 3D, which is an open source tool for building microstructures. If we have knowledge from experimental characterization of microstructures of interest, or from phase field simulations of polycrystals, or microstructures of interest, or any other cellular autonoma, for example, we can build microstructures samples, these statistical volume elements that follow the target statistics, including grain size distribution, spatial correlations between phases like alpha and beta phases in titanium alloys, the disorientation, the minimum misorientation between grains and its distribution. So you can go to whatever measure you desire, things like aspect ratio of grains, to reconstruct microstructures for simulation that adhere to target statistics, with the caveat that when you use a statistical volume element, you're never going to capture the representative statistics. You have to build up an ensemble of such elements to capture the representative statistics of the microstructure. So you can arrive at very complex microstructures. We're doing some work now on additive manufactured materials that have, highly tortuous grains, for example, in this kind of a scenario. You can also admit twin boundaries in addition to grain boundaries. We use crystal plasticity finite element method in our work that involves the classical multiplicative decomposition of the deformation gradient into elastic and plastic parts. This is shown here, F equals FEFP. A viscoplastic rule is used for the slip system shearing rate, typically including a back stress, and it's very important, for example, for precipitation hardened aluminum alloys, such as aluminum 75 T6 that I'll show, and less so for alpha titanium and alpha beta titanium alloys. But nonetheless, we maintain that that's an important element to understand both intragranular and intergranular types of effects. For aluminum 7075 T6, it's of course high symmetry FCC lattice. So we have 12 slip systems, 4 octahedral plates, 3 slip directions each. And for the alpha beta titanium, specifically titanium 6 aluminum type of alloys, 4 vanadium stabilizer, we have 24 slip systems for the alpha grains. The alpha grains are hexagonal closed pack, low symmetry crystals. The basal plane slip is dominant. Prismatic is a fairly easy slip system as well. And we have first and second order pyramidal systems in which the C+A type of pyramidal system plays a dominant role. In the colony grains, which are composed of alternating glass of alpha and beta, secondary HCP alpha, and then BCC beta phase, we use the Berger's orientation relation and homogenized descriptions of the effective response. And that's an active area of research for us and others to understand better the role of the lasts in acicular and lamellar types of colony phases. And so we've published these kinds of models, and I'm not going to spend much time on them. I want to spend more time on talking about the fatigue framework per se. Some of our work about 10 years ago in Craig Prisbala's thesis dealt with duplex Chi-64, which is a particularly fatigue-resistant form used by the United States Air Force because it optimizes fatigue crack formation and somewhat longer crack growth resistance. And it was known experimentally that coarse bimodal low and high primary alpha volume fractions were the worst players in fatigue. In other words, they form fatigue cracks more rapidly than the fine primary alpha form. So that was known, and we were interested in asking the question, can we reproduce with this kind of a strategy known experimental findings over large data sets, statistically large data sets? So this simply shows a plot of the Gumbel statistics shown here. This is the Gumbel distribution at lower right, extreme value distribution. There's also Weibel and Frichet, but the Gumbel accepts arbitrarily large driving force values in this case. And of course, in the cumulative distribution function shown here, the larger values would represent the larger fatigue indicator parameters in the tail of distribution to the right. In other words, they control the minimum fatigue life. So our work focuses more on the tail of the distributions than on the mean of the distribution. You know, in fatigue, we typically talk about means of distributions and then so many standard deviations away. But ultimately, we're typically interested in high value applications of of how far we are from the mean towards the minimum fatigue life. So that's what we're exploring here. And indeed, these computations show that the extreme value distributions are shifted to the right, meaning they have higher driving forces for microstructure C and D as experimentally observed. So that was a promising result. You can see in this microstructure here, we have the light colored primary alpha and the dark colored alternating lass of alpha and beta in the colony phase with about a 40 to 60 volume fraction, 40 to 60% volume fraction of the primary alpha phase. Now, as I mentioned, we're interested then in going one step further in terms of understanding dominant mechanisms to use the extreme value computed locations, the locations of the maximum fatigue indicator parameters or hotspots, and using those locations as marks to then expand in a two-point statistics or radial distribution function around those sites. So we're exploring the question of what is there about these extreme value sites that give rise to these high driving forces to form fatigue cracks. Knowing that, perhaps we can devise a process route that creates microstructures that mitigate those kinds of sites. So this two-point or marked radial correlation function shown here goes out in some expands from the hotspot site out a radius r and looks at the joint probability of having conspiring microstructure effects in the neighborhood of these hotspot regions. It's been done before in composite materials shown at the bottom. So this was very interesting. If you look at these charts, there's a lot here, but basically on the y-axis in each is the probability, the two-point probability of having, for example, a primary alpha basal slip oriented phase next to another one of the same that has a high Schmidt factor. So in other words, two primary alpha grains that are situated next to each other that are favorably oriented for slip. To the right, we have a basal that's next to a phase, a primary alpha phase oriented favorably for prismatic slip, which is another favored slip mode. At the bottom, on the other hand, these two charts at the bottom, we have a basal favorably oriented for slip phase next to a phase that has a pyramidal orientation for slip, a pyramidal A, and to the lower right is a pyramidal A plus C. In other words, we have a basal oriented slip primary alpha grain next to one that's unfavorably oriented for basal, but it has a dominant C plus A type of mode. We have a name for these two scenarios. This one is a large alpha particle. This one is a hard alpha particle. And in the jargon of the literature in fatigue of titanium alloys, those are two names that people often cite. So we have a super particle, a super alpha particle, a large alpha particle versus a hard soft region, a hard alpha particle. And interestingly enough, when you look at these red dashed lines in each chart, those are the marked correlation functions. So it shows the enhanced probability relative to the blue, which is the complete overall microstructure. It's almost like a concentration factor, if you will, of the probability of finding these scenarios at the hotspots. So indeed, we find a very strong probability shown at upper left for two contiguous large alpha particles with a favorable basal slip configuration. And down at lower right, we find similarly a very high probability, the red is above the blue significantly, of finding a basal oriented, favorably basal oriented primary slip alpha next to a C plus A oriented hard mode orientation for alpha. Those are the two that stick out. And those are the two that are almost universally found experimentally, right? So we see these large contiguous alpha cracks and we see these hard alpha particles. And those are the two dominant failure modes. So this gives comfort in knowing that the computations, the microstructurally sensitive computations, are on track or in agreement with general trends of experiments and may be viable, therefore, for comparing microstructures with regard to resistance of these modes. We also found some interesting results in some early work on non-metallic inclusions in nickel-based superalloys. Of course, in powder metallurgy and in casting of ingots of nickel-based superalloys, you have non-metallic particles, and you're interested in knowing how these non-metallic inclusions affect the fatigue resistance, particularly the transition and high cycle fatigue resistance. In some early work of Bill Muszynski, who's now at AFRL, published in International Journal of Fatigue, what he did was to use that small crack growth law, that DADN is phi times FIP minus a threshold value, and fit the results in the low cycle fatigue regime, shown here as the red line, and then predict the high cycle fatigue, okay, to form a crack that extends from the first grain into its neighbors, right? So it's crossed that threshold, the first strongest grain boundary threshold. And in this case, we didn't use a rigorous small crack growth law. We just looked at the probability of extending across the grain due to the driving force of the adjacent grain. Later, I'll talk about small crack growth laws in more detail. But the interesting thing here, and others have found this as well more recently, is that the high cycle fatigue regime, the Baskin's law, if you will, with a shallow slope in stress space or elastic strain space, essentially, is predicted naturally from the same set of relations using the microstructure-sensitive framework. In other words, it's the heterogeneity, the spatial distribution of the driving force in amongst grains in a polycrystal that establishes this transition to a shallow slope. So really, we have these empirical, well accepted laws of fatigue, but then when you do the microstructure sensitive fatigue, those laws sort of become emergent results from the underlying small fatigue crack formation and growth relations. Similarly, shown here at lower right, this is work from a nickel-based superalloy astroloy, heptastroloy, with that's seeded and unseeded with non-metallic particles. These non-metallic particles typically have diameters ranging from about 10 microns to 50 microns. When the inclusions are very near the surface, we have the minimum fatigue life, right? Because you, just like Murakami's argument, you have a square root of area of the inclusion, and then it bridges to the surface and forms a crack very rapidly. So we looked at that in detail by embedding these inclusions into the subsurface at different distances h relative to the grain size. Looked at different inclusion sizes, 20 and 50 microns in this case, into the same representative microstructures. And we were able to then compute, you can see the computational results for without inclusions. This is the square, the dark solid squares with 20 and 50 micron inclusions, and you can see you get a range, right? And compared to the experiments with the seeded and unseeded, the unseeded experiments follow pretty much the computational results in the transition. And with the seeded experiments for an inclusion range 20 to 50 microns, you can see that experiments are also spanning down into this regime. So again, it gives us the capability to look at more realistic size effects and constraint on slip combined with the microstructure scale. Now, more recently, this is work just published in JOM in 2020 by Chris Stopka, a student of mine. Very interesting. Free surface interactions with microstructure. Classical textbooks will say, you know, fatigue is a surface phenomena, and yet, you know, when you look at very high cycle fatigue, cracks often are observed to form in the subsurface because there might be preferred sites that have high driving force in the subsurface in this transition or flip from surface to subsurface. But it turns out that something as simple as the symmetry of slip. For example, we said before, aluminum has FCC crystal structure, high symmetry slip. Titanium has HCP dominance, low symmetry slip. That the manifestation of this is that there's much stronger surface effects on enhancing fatigue crack formation in the high symmetry aluminum than there is in the titanium. So this is a 7075 T6 aluminum that forms cracks by small clusters of non-metallic inclusions, predominantly transgranular fatigue cracks. We've modeled this here with two different ratios of rolled microstructure with crystallographic texture, relatively weak elastic anisotropy for aluminum. And what we see is to the upper right is a significant intensification of the computed FIPS as we move to free surface. So P means periodic, NP means non-periodic, so we have a free surface. And so you can see in both cases, for both an equiax grain and for an elongated rolled grain, loaded strain in the rolling direction, that we have an enormous increase in the fatigue indicator parameter. Whereas for the titanium, alpha beta titanium alloy with various crystallographic textures, that's not the case. In fact, here we see almost the same fatigue indicator cumulative distribution functions for the two cases, with and without a free surface. And indeed, experiments show more subsurface fatigue crack initiation in titanium alloys than in the high symmetry case, which is much more prominently investigated. We've considered a number of applications with this kind of framework in the last, probably 12 or 13 years. Process-induced defects, pores, intermetallic and non-metallic particles. We've looked at cast dendritic structures going back to the year 2000 to 2003 in cast A356T6 aluminum alloys. We've looked at the observed enhancement of fatigue crack formation in the presence of sigma-3 twins and nickel-based superalloys. And that comes out naturally as an interplay between the intensification of slip due to the elastic anisotropy associated with the twin and the standoff distance interaction from the twin. We've looked at shot peening effects, the effect of refined microstructure near a surface subjected to high shear, modification of the chemistry in order to affect particle debonding versus particle fracture, because the two are quite different in terms of their enhancement of the local slip around these particles. We've also looked at size effects of notches, the notch factor, K sub F, fatigue notch reduction factor, considering microstructure, and whether we can predict that with these kinds of strategies and tailor that with these kinds of strategies. And as we've just seen, surface versus bulk fatigue crack initiation, we're now working on a 316L stainless steel with Navy support, looking at additive manufactured material. I wanted to mention a little bit about multi-axial fatigue because, this framework that I'm talking about is useful not only for comparing microstructures for a given loading condition, maybe uniaxial loading in the previous examples, but oftentimes when we have limited test data, maybe we have shear data, maybe we have some uniaxial data, we then have to go to a component that has combined stress states and make some estimate. Maybe it's a science criteria or some kind of critical plane type of approach we're using. But we can actually compute over wide ranges of strain and stress state, and we can map out the ISO fatigue indicator parameters. And we choose the Brown and Miller plane. Keith Miller, Mike Brown introduced the so-called gamma plane in 1973, where you have case A and case B. Case A would be like shear loading, where the cyclic shear is in the bulk direction. Case B, the cyclic shear disrupts the surface plane, and that would be typical of ranging from uniaxial to equibiaxial conditions. And you'd have these typical contours. This is a plastic strain gamma plot for an aluminum alloy by Ellison and Andrews. And it just shows the case A contours are distinct from case B. So we go from the x-axis here is pure shear. This is the uniaxial bound, and then this is the equibiaxial bound. This encompasses all strain states that are accessible. Well, we compute for 7075 T6 the fatigue crack indicator parameters for different textures, different crystallographic textures. This is an equiax case for a given structure. And we do this over a range of loading conditions: pure shear, equibiaxial tension, uniaxial tension, and in between. You see all these data points. Then we use a machine learning algorithm, so-called Gaussian regression, to tell us the uncertainty associated with these estimates, and it defines the next point to compute. So with a relatively low number of computations, we can map out the gamma plane, right? This is valuable because if we then have an experimental correlation for a given condition, we're able to assert the multi-axial fatigue criteria for a given microstructure, not just for a class of materials like aluminum alloys, et cetera, but for a specific type of aluminum alloy or titanium alloy. I also wanted to mention some work that we've done on microstructurally small fatigue crack growth, because obviously if we want to probe up into the fatigue crack initiation regime, it's not enough to know just the probability to form a crack in the nucleate phase, but you'd like to know how it grows through the microstructure. To that end, I'd like to share a few slides with some work by Gustavo Castelluccio, who's now at Cranfield University in the UK, in his thesis, circa 2014, 2015. When we actually evolved cracks, allowed them to grow and did the computational simulation, which is quite arduous, we would see a characteristic decay of the surrogate driving force in each grain as a crack group. That's shown by these clusters of points right here, showing the decay, and it's fit reasonably well by these dark black lines, and we renormalize to the FIP at the beginning of each increment of growth through each successive grain. So it's a renormalization process for each successive grain, and using this kind of analytical estimate that's calibrated to these results is useful because it allows us to then achieve an analytical form for the life, the number of cycles required to propagate a crack across a given grain, right? We used a Murakami square root A type of assignment for the crack size in this case. And so I'll not go through the details, but using an incubation law that depends on the FIP, sort of a la Coffin-Manson relation applied at the damage process zone size, we can then apply a few loading cycles, determine the FIPs after shakedown, after cyclic elastic plastic shakedown, compute the band with the shortest nucleation life. Then we grow the crack across that grain using these analytical relations. We then compute a few cycles to shake down and redistribute the cyclic plastic stress and strain fields, and then extend over the next grain, et cetera, up to 30, 40, 50 grains of extension. And in the process, this incorporates both plasticity and roughness-induced closure, right, which are very difficult to consider in classical elastic plastic fracture mechanics calculations of small cracks. Now, a couple of key findings. One of the most important ones is that we find characteristically that the DADN versus crack length relation is nearly linear through the first few grains of propagation. And this was widely observed in some of the early literature on microstructurally small fatigue cracks, for example, from Japan in the 1970s, 1980s, and others. Even though there's nothing in our relationship to suggest this, we're using just what I would call a physically based DADN versus cyclic crack tip displacement surrogate driving force measure, and arriving at this as an emergent result from a microstructure, right? And moreover, we're able to predict mean stress effects that depend on the microstructure. So, for example, we found some results for steel that mimic something that Keith Miller had found with Smith on steels. Now, I want to emphasize that what I've talked about so far has really focused on a relative comparison of different microstructures in terms of fatigue resistance. That's where we see this technology as being most applicable right now. We can envision it as well to augment experimental strategies to identify dominant fatigue mechanisms at different amplitudes and stress states. Of course, it has a major role in estimating statistical variability of fatigue response as a function of microstructure, and also on projecting effects of microstructure in combined stress states. We've seen that it can evaluate the sensitivity. It's kind of a rational sensitivity analysis of the fatigue response in terms of effects of inclusions, pores, and residual stresses, all of which, for example, in additive manufacturing are terribly important, but even in subtractive. And then combined effects of notches and surface conditions with microstructure, including size effects. Peterson's equation, for example, is known to have different values of a constant A, which depends on microstructure, and that's what is manifested here. So I would emphasize that we don't maintain that it's yet at the stage of certainty that allows us to do predictive lifetime estimation based on these kinds of simulations. It always has to be calibrated for that purpose. But still, it has its role. Now, one of the weaknesses, I would say, of this kind of an approach is that it's very computationally intensive, and there's uncertainty in the local phase information in the models, and the crystal plasticity simulations are expensive. So we've extended the approach recently, the last 3 or 4 years, using Kroner's localization approach. I'll not spend much time on this, but suffice it to say that we use a microstructure function to incorporate the role of the orientation of phases, and an influence function is a pseudo Green's function approximation that's fit to finite element crystal plasticity, finite element results. And we use those together in order to achieve dramatic speed up. I'm talking a factor of 20,000 speed up in the estimation of the local responses, the local cyclic plastic strain tensor and fatigue indicator parameters for microstructures. This is a alpha titanium situation scenario comparing in the left column this material knowledge system based on the Kroner methodology with the finite element case. The maximum errors are only 1% or 2%. With this kind of a strategy, we can then really do a rapid comparison of different microstructures. So these are a number of textures for Ti64, and of course in low symmetry titanium alloys, texture plays a dominant role. And then using this strategy, we can generate the sets of microstructures. We can rapidly evaluate them, not using crystal plasticity finite element anymore, but using the Kroner type strategy, and then compare the cumulative distribution functions for the maximum fatigue indicator parameters. And interestingly, when we do that, this is for alpha titanium. Shown at left is the extreme value distribution functions based on the full-blown crystal plasticity finite element simulations, and shown at right are the same extreme value distributions for the 20,000 times faster Kroner methodology, right? And again, this is expressly for high cycle fatigue regime, so constrained microplasticity, not for low cycle fatigue. And more recently, we've adapted a machine learning algorithm for the materials knowledge system, which takes the user out of the loop, so to speak, and requires less expertise in estimating the influence functions by using Gaussian regression for that. I had alluded to uncertainty. So uncertainty plays a key role, as you've probably gathered in the presentation. The microstructure itself has randomness. Our models have uncertainty, both in the form of the model and the parameters of the model. The experiments have uncertainty that has to be quantified. And if we propagate that through process structure property relations, the idea is that if we choose the dominant set of processes and then information at the structure scale and then project using these microstructurally sensitive schemes onto multiple properties of interest, maybe yield strength and minimum fatigue life, if we have a range of microstructures, we should have ranges of these properties, right? And even minimum fatigue life has a range, right? It's not just some deterministic computed value. We pursue this using a combination of distribution functions and interval probabilities as per work by Sandia National Laboratories. We've interfaced a lot with Laura Swiler that has a nested epistemic aleatory type of approach for the uncertainty. Whereas epistemic, it's a reducible uncertainty that we can reduce with improvements of model and experiments. And the aleatory is just simply the random. Now, the important takeaway here is, before I showed these extreme value distributions of the Gumbel distributions of the fatigue indicator parameters, but here we're using lower bound and upper bound estimates that in and of themselves have bounds, right? So the intervals, the solid red and blue lines are the upper and lower intervals based on sampling a number of statistical volume elements representing the aleatory or random uncertainty, whereas the model uncertainty, the parameter uncertainty, are based on the red versus the blue points. So you can see that we can then bound the computed extreme values distributions that control minimum fatigue life, shown by the red and the blue, and we can bound the estimates according to the random uncertainty of each. So a combination of distribution, probability distributions, and interval probabilities. So this then rewrites, to some extent, the original algorithm that I presented earlier, where we consider the uncertainty propagation, and we can identify places in the entire framework where we need to reduce uncertainty. For example, maybe we need to run a few more experiments of a very specific type, or maybe we need to do a confirmation of a mechanism that's suggested from the calculations. Maybe we need to improve the models or the estimate of model parameters. Those are all features in this kind of a framework that need to be explored. Some horizons that I'd like to mention. First of all, sampling strategies, the way we threshold the fatigue indicator parameters, the prediction of the maximum fatigue indicator parameter for large critically stressed volumes. Maybe we have a number of simulations and we have a large notch and we're interested in predicting the interval probability of minimum fatigue life for that. Obviously, refinement of modeling at various scales using other approaches like molecular dynamics, discrete dislocation dynamics that feed up into the fatigue indicator calculations, linking experiments and computation versus data science, and multi-physics and chemomechanical effects. We're doing some work now on multi-physics, chemomechanical effects that sort of highlight the desirable aspects of microstructure simulations. When you do fracture mechanics with chemomechanical effects, consider a mechanical process zone and a chemical process zone. And it's a little unwieldy to rectify those, but when you're doing the physics based on direct computation of microstructures with the transport and the mechanical effects coupled, it's very clear, right? And I'd just like to mention too that next generation coupling with experiments is very important. And one of the most exciting things we see now is the movement towards in situ diffraction experiments, large scale diffraction experiments that can measure the formation and growth of cracks in microstructures, including where the crack arrests, where it grows, pathways, transitions between transgranular and intergranular growth. And that kind of information has very large data, and the data need to be fused. The experimental data needs to be fused with the computation. And the best way to do that is through machine learning algorithms. And so a really hot area of focus now is data fusion with Bayesian updating to handle the uncertainty associated with that fusion, to really understand what elements of the model are need to be refined in order to agree with the physical observations, and at the same time understand how the experimental strategies need to be improved in order to deliver more high value results to understanding. So I think I'll close with this slide.